So this video deals with quite an important concept in equilibrium, certainly from a qualitative point of view, and that's this concept of Le Chatelier's principle. So Henri Le Chatelier was quite a famous French chemist, and he, amongst other things, was very involved in mining and mining research, but also worked on thermodynamics and established some laws or rules for systems at equilibrium. And he's probably best known for that, namely Le Chatelier's principle. So without further ado, let's start looking into Le Chatelier's principle. So here it is stated. So if a dynamic equilibrium is disturbed by changing the equilibrium conditions, the system undergoes a change in a direction that counteracts the influence of the change, that initial change, and if possible, returns the system to a new equilibrium. So in a nutshell, or simplified, I guess we can look at it, we can an equilibrium can be stressed. So we stress the equilibrium system, and it will respond to minimize or counteract that stress. So there's a variety of ways we can stress an equilibrium or cause it to be changed. And so the first one there, because we've looked at equilibrium expressions in terms of concentration, one thing we can do to equilibrium systems, we can change the concentration of all of the constituents. So either products or reactants. And that's pretty easy to do with gases and aqueous systems. A little harder to do when you're looking at liquid systems, but we'll look at examples of that in terms of gases. Another way we can change or stress an equilibrium is to change the temperature of the system. And that should be fairly evident to you, considering most, if not all, reactions have a thermochemical component to them as an associated delta H. So if we change the temperature of the system, it will respond in a predictable way. And lastly, we're going to look at the effect of changing the volume. And again, this is primarily from a view of gases. So we change the volume of the system. And I'll get into that when I'll explain that when we get to that particular component. So we're going to look at these three different stresses, they would be called, and we're going to identify how the equilibrium responds to those stresses. So first of all, the effect of changing temperature. Well, effect of changing concentration. One thing you want to make sure you realize is how can we change the concentration, and say specifically with a gas. Well, here I have gases in a container. It's a sealed container, so the concentration of that gas is going to be some amount, and typically that's moles per unit volume. And so typically for us that's liters. So that gas will have a known concentration in that volume. Well, can I change the concentration of that gas in that container? And it's pretty easy. Of course I can. I can just start increasing the number of particles, and there I go. So now I've increased the concentration by increasing the amount, the number of moles, per same volume. So I haven't changed the volume, but I've changed the amount. And obviously you realize we can reduce the number of particles as well, and if we do that, we would reduce the concentration. So that's how you affect a change in concentration in, say, a gaseous system. You can also do that in aqueous systems by adding different ions to the solution that way. So an increased number of ions per solution. Again, as long as the volume stays the same, you would affect a change in concentration. So let's look at how Le Chatelier's principle works when we change the concentration. So here's our equilibrium system. Hydrogen gas plus iodine gas yields hydrogen iodide. Now, what's important about Le Chatelier's principle, I think, is how you frame your answer, how you sort of work out your answer based on the information given. So here's our information given. What will happen to the position of the equilibrium? So that's the way the equilibrium is going to shift if the concentration of iodine, I2, is increased. So here's how I recommend you solve this problem. You state the stress. So the stress in this case is increased concentration of I2. So there I've stated my stress. That's the stress. Now Le Chatelier's principle says I'm going to counteract that stress. So I would counteract the stress in terms of the constituent that is being changed. That is the constituent that causes the stress. So Le Chatelier's principle says the equilibrium is going to respond to counteract that stress. A counteracting of increased I2 is a decrease in I2. And now you state the shift. And so that's a direction, and it's going to shift. And which way is it going to shift? Well, now I just have to look at my double arrows, and I look for the arrow that gives me I2 as a reactant. So I2 is a reactant as written. So I2, to try to decrease the concentration of I2, I need to interact hydrogen with iodine. So the equilibrium is going to shift to the right. So increased I2 as a stress will cause this equilibrium shift to try to decrease I2 as a shift. And that shift then, from a directional point of view, is a shift to the right. So what will happen to the concentration of hydrogen iodide when the concentration of iodine is increased? So again, if my shift is to the right, then I'm producing hydrogen iodide. So the concentration of hydrogen iodide will increase as a result of an increase in the concentration of iodine. So here's another question. What will happen to the position of the equilibrium if the I2 and position of the equilibrium and the concentration of I2 if HI is decreased? So again, here's my stress, decreased concentration of hydrogen iodide. My shift in terms of that stress is equilibrium is going to try to increase the concentration of hydrogen iodide. And so how do I increase the concentration of iodide? Well, I still shift to the right. I'm going to if I shift to the right, if the reaction proceeds to the right, I produce hydrogen iodide, I increase its concentration. And if I shift right, what happens to the concentration of I2? Concentration of I2 decreases. So there is how you deal with concentration changes and Le Chatelier's principle. And again, just to remind you, state the stress, state the effect of that stress on the constituent of the stress, according to Le Chatelier's principle, and then state the shift. And afterwards, if you are asked other questions, you can relate it all based on your shift. All right, let's have a look at something else. So the effect of changing temperature. So here's a particular reaction with the thermochemical term included. And so one thing it's important, I think, or very useful to do in terms of Le Chatelier's principle is make sure you have the equation with the thermochemical term as part of the reaction. That just gives you a lot of a really useful visual in terms of heat. And so because it's a negative delta H, it's exothermic. And so heat is produced, and so there's heat included in my equation as a product of the reaction. And so that is an exothermic equation. And now we can have a look at some questions. So what's going to happen to the position of the equilibrium and the concentrations of both carbon monoxide and methane gas if the temperature of the system is decreased? So like we've just done, State the shift, state the stress. The stress is decrease in temperature. State the shift in terms of the stress. Well, if I decrease temperature, Le Chatelier's principle says the equilibrium will respond to try to counteract that stress. The equilibrium will try to increase temperature. Now you just have to look at your thermochemical equation and see which way this reaction needs to proceed to increase the temperature, to increase heat. And again, we would then drive the exothermic process, so we're going to shift to the right. So that shift causes increased heat, increased temperature by producing 230 kilojoules of energy. So the shift will be to the right. So if the shift is to the right, what happens to the concentration of carbon monoxide? Shifting right, carbon monoxide concentration will decrease. Shifting right, the concentration of methane will increase. Okay, so there's a stress and shift response caused by temperature change. So here's another one. What will happen to the temperature if carbon monoxide concentration is decreased? So back to a change in concentration. So there's my stress, decreased concentration of carbon monoxide. Le Chatelier's principle says the equilibrium is going to respond to try to increase the concentration of carbon monoxide. How do I increase the concentration of carbon monoxide? I shift left. So if I shift left, I'm driving the exothermic reaction, so I'm driving the endothermic reaction, so temperature would decrease, right? The endothermic process is the process being engaged here. I'm shifting left, so I'm using heat energy, so temperature is going to go down. So that's Le Chatelier's principle in terms of temperature change. All right. How about a pressure effect? A volume effect. And as I'm going to show you, a volume effect we really have to look at as a pressure effect. So have a watch of this.
So here I'm going to show you the effect of changing the volume of a gas and how the equilibrium might respond. So here we go. Here's the syringe, and notice the volume and also notice the pressure above. So I'm going to decrease the volume first. So their volume is decreased to a new fixed volume, and you notice pressure goes up. So that's Boyle's law, which we talked about last year. And the important thing is it's a new fixed volume. So the stress on an equilibrium is a decrease in volume. It cannot respond to try to increase the volume back. It doesn't respond by changing the volume. So if it can't change the volume, it responds by trying to change the pressure. So if the stress is a decrease in volume, the stress is translated to an increase in pressure. And so Le Chatelier's principle says the equilibrium will respond by trying to decrease the pressure. So a volume stress is converted to a pressure stress. And we can look at it the other way. I can increase the volume and watch what happens to pressure. So I've increased the volume of the gas. Pressure goes down, again according to Boyle's law. And so the stress on the equilibrium is a decrease in pressure caused by an increase in volume. And so the equilibrium will respond by trying to increase the pressure.
So hopefully, as you see, a stress in terms of a volume change really needs to be looked at in terms of a stress in terms of pressure, because the volume cannot be changed back. So let's see how this is going to work. So here's our system at equilibrium. We have 2 moles of nitrogen dioxide gas yielding 1 mole of nitrogen gas and 2 moles of oxygen gas. And so here's the question: what will happen to the position of the equilibrium if the volume of the equilibrium system is decreased? So here's our stress, a decrease in volume. Well, let's have a look at another short little video that hopefully explains how you can change pressure using particles, because that's really the root of what we have to do.
So what is it exactly that causes pressure? Well, I hope this little demonstration is going to drive that home for you. Here we have a container, and currently the pressure is 0. Why is the pressure 0? Because there's no matter in there. There's no particles in there colliding with the walls of the container to generate that pressure. So we have to add particles. I'm going to start adding particles. So here we go. There's about 40 particles, and I can already see we're starting to generate a pressure. We'll let that go for a few seconds so the pressure equilibrates or sort of reaches a steady state. And there it looks kind of steady between 0.19 and 0.21 atmospheres. So there we have it. Particles cause pressure. So what happens if I increase the number of particles? Well, let's triple the number of particles. So now I have about 120 particles. Definitely quite a bit more crowded in there. And lo and behold, the pressure goes up. Well, of course the pressure goes up. I now have more particles, more frequent collisions with the sides of the container. That's where pressure is being measured. So pressure must go up when I have more particles. More particles, greater pressure. Let's take that back down again. Fewer particles, and the pressure is less. There's fewer particles, and the pressure has come right back down. And we see that the pressure's come down because there's less particles striking the walls of the container.
Okay, so there we have it. We can affect pressure changes by increasing or decreasing the number of particles. And so we have a ready-made solution of that in our balanced chemical equation. So here's our equation again. 2 moles of nitrogen dioxide yield 1 mole of nitrogen and 2 moles of oxygen. From a particle point of view, 2 particles react to yield 3 particles. That's a change in the number of particles, and that's how we're going to shift the equilibrium. So again, let's go through this process. What will happen to the position of the equilibrium if the volume of the system is decreased? So again, here's my stress, decreased volume, which we now need to equate to a change in pressure, increased pressure. So there's my stress. It's actually an increase in pressure. So Le Chatelier's principle says I'm going to shift the equilibrium to try to reduce pressure. And so how do I reduce pressure? I need fewer particles in the system. I need to remove particles from the system by driving my reaction in one direction or the other. If I drive my reaction to the right, 2 particles yield 3 particles. That's not a reduction in particles or a reduction in pressure. If I drive the reaction to the left, 3 particles become 2 particles. So I'm going to shift to the left to produce fewer particles and reduce the pressure. So that's how a volume / pressure effect is dealt with. Let's have a look at another example. Okay, so same process. We've decreased the volume, so the shift is still to the left. What will happen to the temperature? Well, if we shift left, we're driving the endothermic process, negative delta H. That's an exothermic reaction. A shift to the left is endothermic, so temperature would decrease. And one more example. What will happen to the concentration of nitrogen dioxide if the volume is increased? Okay, so here's our stress, increased volume, which equates to a decrease in pressure. My shift is going to be to try to increase pressure. My shift is going to be to the right to produce more particles. So I'm shifting to the right, 2 particles becoming 3 if I go that direction. And so what happens to the concentration of nitrogen dioxide if I shift right? Concentration of NO2 will decrease because I'm driving the forward reaction. And so that's how volume effect is dealt with in terms of Le Chatelier's principle. All right, just about finished. What about if we add a noble gas such as argon to a system? Well, first of all, just remember what we have here. In essence, we have a mixture of gases in a container, and we can say this is nitrogen plus oxygen yielding nitrogen dioxide to put some chemicals to it. And so the blue nitrogens and the blue oxygens and the red-blue nitrogen monoxide molecules are all mixed into the system. Now, what's the pressure of that system? Well, you have a total pressure, P tot. We've talked about this last year, and what that equals is the partial pressures of all of these reacting gases. So at equilibrium, you're going to have a certain number of each particle, and that particle is exerting a pressure, so the partial pressure of nitrogen, for example, is going to equal something, and the total pressure is the sum of all of them. So if we add a noble gas, let's see what happens. So the noble gas, noble gas is going to enter the system, and you're going to get more particles. So what's happened to P tote? P tote has actually increased, right? Because now we have P argon plus PN2 plus PO2 plus PNO2. So P total has increased. But is there any change here? We have the same reacting gases, nitrogen, oxygen, and nitrogen dioxide, and we haven't changed them. Argon does not react with these gases. So argon will not influence the partial pressure of those three gases. So even though total pressure is increased, the partial pressure of the reacting gases has not changed. So there is no change to the equilibrium. So addition of a noble gas does not cause a shift. So it doesn't change the position of the equilibrium. And that applies to any non-reacting gas. We mostly look at noble gas because they're the least reactive of all gases. But if you could add some other non-reacting gas, the total pressure would certainly go up because you've added some gas to a volume. But the partial pressures of the reacting gases have not changed, therefore the equilibrium has not changed. How about adding a catalyst? So if we add a catalyst, we know what happens. If we have, again, a generalized reaction, A plus B yielding C plus D, and vice versa as an equilibrium, so the addition of a catalyst affects rate. So it affects a rate increase, but for both reactions. So adding a catalyst does not change position. You just get there quicker. So a catalyst has no effect on position. So the equilibrium will not shift based on the addition of a catalyst. So, Le Chatelier's principle. We've looked at changes to concentration and how a system responds. We've looked at changes to temperature and how a system responds. We've looked at changes in volume, which you equate to a pressure change, and how the system responds. And we've looked at a couple of additions to an equilibrium system that do not affect a change in position. So that's Le Chatelier's principle, and that concludes this video.